Welcome to EDU World Space.
Problem 8.47. We have two masses on a frictionless table, mass A and mass B. They have these ideal spring bumpers on them so that the collision is ensured to be perfectly elastic. A is moving towards B at 2 meters per second initially, and B is standing still. And some things we're asked to find out are what's the maximum value of the potential energy stored in the springs, and then what is the speed of either block when that is the case, when the maximum potential energy is being stored. And then after the blocks bounce apart, what are the speeds and directions of either block? So we can use the conservation of momentum, because that's always true, to find what the speed of the two blocks is when they're moving together with the maximum potential energy in the spring. And they're going to be moving together at the same speed, because if they had any motion relative to each other at that moment, they wouldn't, the spring wouldn't be compressed all the way, because the relative speed is going to decrease, and then when it has a minimum is going to be where the maximum potential energy is. And then when the speeds relative to each other increase again, that's going to be coming from the energy that was stored in the springs. So to find their combined, or the speed of both of them when they're moving together with the maximum potential energy, we use the conservation of momentum. And since they're moving together at the same speed, they behave as one mass, with the total mass equal to the sum of their individual masses, and we'll just call this speed v. Solving that for v, we see that they're moving together at 0.333 meters per second. So now the initial kinetic energy, because of the conservation of energy, because this is totally perfectly elastic, the conservation of energy says that the kinetic energy of A initially has to be equal to the sum of the kinetic energies of A and B combined, plus the potential energy stored in the springs. So now we know how fast the combined A and B are moving. So we know this, and of course this is part of the setup of the problem we're just given. And so the potential energy is just the difference in the two, because that's where the energy has to have gone. So then this would be 1/2 ma va initial squared minus 1/2 total mass times the speed that we just called v squared. And then the energy that must be stored in the bumpers is then 3.33. Well, it works out to be 3 1/3, but we only want 3 joules. And so that's how much had to be stored in the bumpers, because they still have to be moving together to conserve momentum. Otherwise, it would be quite easy if they were moving, if they had equal masses, or they're just moving together towards each other with the same momentum, then they would be at rest when the spring is compressed to the maximum extent, because the net momentum would be 0, and so when they're sort of a combined object, they would have to not be moving. But in this case, since this is stationary, there's not even any question of whether their momenta are equal and opposite. So then for part B, this is a fairly simple, just elastic collision conservation of momentum thing now. And just using the formulas that are in the chapter without going through how you derive them again. I mean, it's the same sort of thing as, everything we've done before. You just set up a slightly different conservation of momentum expression, because, well, and also the conservation of energy, because you'd have one equation and 2 unknowns, and that doesn't do you much good. And then you can use the conservation of energy to give you your second equation and then solve them, and that's gone through in the chapter, and we don't need to go through all of that again right here. So then this is the equation that the chapter shows how to derive. It's the ratio of the difference of the masses to the sum of the masses times the initial speed of A. And so then this gives us negative 1.33 meters per second. So A has reversed direction. This is sort of what you would expect, because it doesn't have, it has a smaller mass, which is, sort of exactly what this term here is saying. And so it's going to be bounced completely back in the direction it came. Because if this had a larger mass, then it would be able to impart enough momentum to B that B would shoot off at a faster speed, and A would continue going in the direction it started in. And this looks very similar, except A and B are interchanged everywhere. Oh, no, I'm sorry. Thinking of the wrong thing. This is 2ma over m a plus mb times the initial speed of A. And so then this works out to 2/3 of a meter per second, or 0.667.